All right, so we are solving systems of equations by substitution, and now let's look at what possible outcomes we could have. Remember these outcomes from when we did graphing. We might have our lines crossing, so we'd have one solution. We might have our lines being parallel, which means no solution, and we might have coinciding lines, which means infinite number of solutions. Now when we were graphing, those weren't hard to see. If the lines cross, I knew they were going to cross because I'd have different slopes. If the lines were parallel, I was putting these lines in slope-intercept form. I could see if they had the same slope, and if they had the same or if they had the different y-intercepts. But now that we're solving with substitution, we're not only not graphing them, we're not even putting them in slope-intercept form. So how on earth are we going to know if the lines are parallel or not? Well, we have exactly the same three outcomes, which makes sense. It should make sense since we're just doing the same problem in a different way. But we're just going to recognize those outcomes in a different way. If the lines cross, then basically, if you try to solve it, you'll get an answer. So those are the two problems we've already done, is we just got an answer, so the lines crossed. If the lines are parallel, all the variables are going to cancel while you're solving, not while you're checking. Remember that from chapter 2. All the variables cancel while you're solving, and what's left is false. That will tell you that you have no solution. And what's going on behind the scenes is parallel lines. If all your variables cancel while you're solving, again, not while you're checking, while you're solving, and what's left is true, that means that you have an infinite number of solutions. What's going on behind the scenes is coinciding lines, but you probably won't recognize them as coinciding lines since you're not graphing them. So just know if all your variables cancel, you'll either have no solution or infinite number of solutions. It just depends on whether you have a true statement or a false statement. So let's look at some examples. Okay, for this guy, first step, solve for one variable. Again, pay attention to what's easiest to solve for. Well, nothing looks great. That y in the second equation looks passable, but I'm still going to have a fraction, but let's do that one because it's not that bad. So solving for y in the second equation, I'd add 5/2 x to each side, so I get y equals 5 plus 5/2 x. You may have noticed that now that I'm not graphing things, I'm not as particular about keeping the x term first and writing it as 5/2 x plus 5. If you want to, that's fine, but I just don't care so much when I'm not graphing anymore. Okay, I've got one variable by itself. What do I do next? Okay, I look at the other equation. So since I solved for y in the second equation, I'm now going to rewrite the first equation. Since I got y by itself, I'm going to leave a space for y. So I have 5x minus 2 space equals 6. And since y equals 5 plus 5/2 x, that drops right in there. Now I distribute, so 5x will stay the same. Negative 2 times 5 will be negative 10. Negative 2 times 5/2. Those 2's will cancel, so I would just have minus 5x equals 6. Just look at the distribution, make sure it makes sense. Negative 2 times 5 gives me negative 10. Negative 2 times 5/2. Negative times positive is negative. The 2 cancels with the 2 on the bottom, and I'm left with the 5x. Now combining like terms, 5x minus 5x, that cancels. I was in the middle of solving. I'm not checking. I'm in the middle of solving, and all my variables went away. So if I'm in the middle of solving and all my variables are gone, I look at the statement that's left. Negative 10 equals 6. Is that true or false? That's false. That says these lines cross when negative 10 equals 6, which is never. So the lines don't cross. They're parallel. So my answer is no solution. Okay, let's do another one. Do this one on your own. Pause the video and then come back. Okay, now, while you were doing this one, did you have trouble knowing what to solve for? It may not have looked like there was a home run because all of those variables have coefficients. But there are a couple of things that are easier than a couple of others. For instance, look at the first equation. Yes, if I solve for x, I'm going to have to end up dividing by 3. But look at the other terms. They happen to be divisible by 3. So I'm not going to end up with fractions after all. That would be a really good choice to solve for x in the first equation. What if I solve for y in the first equation? I'd have to end up dividing everybody by 6. Well, that's not a problem for the 6 that's on the right-hand side of the equal sign, but 3 divided by 6, that's going to give me a fraction. It won't be wrong, but it's just a little more work. Same thing for the second equation. It's easier to solve for x than it is for y. So let's solve for x in the first equation. I get 3x equals 6 minus 6y by subtracting 6y from both sides. Now I don't quite have x alone. I want to divide both sides by 3. 3x divided by 3 is x. 6 divided by 3 is 2. And negative 6y divided by 3 is negative 2y. So I've got x equals 2 minus 2y. Now what do I do with that? Okay, I plug it in place of x in the other equation. So I'll rewrite that second equation, but instead of leaving a big old space for y, I'm going to leave a big old space for x, because that's what I solved for. So I have negative 6 times, big old space, minus 12y equals negative 12. Now I left that big old space there because there used to be an x there, and I want to put a 2 minus 2y in there. Next thing I'll do is distribute. Negative 6 times 2 is negative 12. Negative 6 times negative 2y is positive 12y. Subtract 12y equals negative 12. Combining like terms, again, all my variables evaporated. That's okay. I was in the middle of solving. If all my variables cancel while I'm in the middle of solving, then I've either got parallel lines or coinciding lines. This says these lines cross when negative 12 equals negative 12, which is all of the time, so they're always crossing. So I have an infinite number of solutions. Okay, let's do this last example. 4x plus 3y equals 4. Negative 2x plus 5y equals negative 2. Okay, this one is one that, again, doesn't have a clear-cut, perfect thing to solve for. Now I'm going to actually solve for x because if I look at that, if I divide, I've got 3 terms there. If I divide them by 2, it's going to work for 2 of them but not for 1. So that makes my life a little bit easier. So dividing by negative 2, I get x is equal to 1 plus 5 halves y, which kind of stinks, but it still works. It's okay. So I rewrite the first equation, leaving a big old space for x. So I have 4 times what x used to be, plus 3y equals 4, and then I drop that guy right in there. Now I distribute, so I have 4 plus 10y plus 3y equals 4. Combine like terms. Subtract 4 from both sides. Now if I divide both sides by 13, what will happen? Remember, 0 on the top of a fraction is fine. 0 on the top of a fraction is just 0. It's when we have 0 on the bottom of a fraction that it's undefined. That's when we have a problem. So I have one variable. Where do I plug that 0 in? 3 correct choices. I can plug it in the first equation or the second equation, but the easiest place is to plug it in where I already solved for x. X equals 1 plus 5 halves y, so x equals 1 plus 5 halves times 0. 5 halves times 0 is 0, so x equals 1. And for a nasty looking problem, it has a very pretty little answer. And if I plug it in, it works. Okay, the next thing we'll do are very simple story problems. You'll have harder ones later on, so just be grateful for these easy ones.